All right, so let's begin our introduction into 7.1, and we're talking about antiderivatives. So up here in this first line, we have the definition of what an antiderivative is. And it says if f prime of x equals lowercase f of x, then f of x is an antiderivative of f of x. So that is our definition for antiderivatives. And I want you guys to challenge yourselves by trying to put the definition into your own words after listening to the rest of the video. So that will be a challenge to you all. Put the definition for your antiderivatives into your own words. So looking at some of our examples based on our definitions, try to make a little bit more sense of it. It says if you have a function and it equals 5x, then the derivative of that function is f prime of x, which equals 5. So the original function, which is f of x, which is 5x, is an antiderivative of the lowercase f of x, which equals 5. B is another example. You have an original function, which is x squared this time. Its derivative is 2x. So that means the original function x squared is an antiderivative of 2x. And then here, there's just a little note. Your original function, which is usually written with a capital letter, is the antiderivative. So an original function is the antiderivative of its derivative. However, consider a couple functions that we have here. We have g of x equals x squared plus 1, and h of x equals x squared plus 8. If you take the derivative of both of these two functions, they both have the same derivative, which is f of x equals 2x. The derivative of g of x is going to be 2x because the one is going to go to 0, and the derivative of h of x is going to be 2x because this 8 will also go to 0. In fact, any function that can be written in this format where you have x squared plus some constant is going to have 2x as its derivative. Therefore, all of the functions that are antiderivatives of f of x equals 2x is given by this equation, f of x equals x squared plus c. We call this general equation a family of antiderivatives. So you have a general equation for antiderivatives when you have the constant c that's added in. The family of all antiderivatives of any function is always going to be indicated by the antiderivative of the function plus some constant. Now let's talk about what each part of the symbol of the expression means. So you have your integral sign, which is your stretched out x. You have what is the integrand, or the function that's being integrated. And then you have the entire expression together, which is the indefinite integral. And then the antiderivative is the answer that you get on the other side after working it out. So ultimately, finding your antiderivatives is the same as finding the reverse of finding your derivative. So when we have 2x, we know that this 2x is the derivative of x squared. And then we add on some constant because we don't know what the original function exactly was. So we always say that it's going to be the antiderivative plus some constant when we evaluate these indefinite integrals. So another example, you have the integral of 5x to the 4th power dx. And then that equals x to the 5th power plus c. And the way that you check to make sure you did it right, well, you always just take the derivative of your antiderivative. If you take the derivative of this expression, you get 2x plus 0, which is just 2x. So this is correct. If you take the derivative of x to the 5th power, you get 5x to the 4th power. So this is correct. And then here's just a visual. Again, when you find the derivative, you're going from that original function, and then you end up with the derivative. Notice that the constant disappears because the derivative of a constant is 0. And then if you're going in the opposite direction, that's when you're finding the antiderivative, and you have to add the c back in. So you start with the derivative, and then when you find the antiderivative, you're going back to the original function. So now looking at some rules, and as you guys practice with this, it'll kind of become like second nature, just like you have it down to second nature when you guys are taking the derivatives. But now we're just going in the opposite direction. So when you have a power function, we're using the power rule. As long as n is not -1, then you have x raised to some power. So when you do the antiderivative, you're going to increase the exponent by 1, and you'll be dividing it by your new exponent, which you added 1 to. And then, of course, you still have plus c tacked on at the end of it. So another way of writing it is that you're going to have 1 over your new exponent after adding 1 times x to the n plus 1. So you're just adding 1 to your exponent this time, instead of subtracting when you find your derivative. So, and then of course you always have plus c added on to the end of it. And then here are just some examples. We had x to the third power, we increase the exponent by 1, and we divide by 3 plus 1, and we add c, so that became x to the fourth power over 4 plus c. And it works the same way. If you have a radical function, you just rewrite it as a power function. You show what the exponent is. So we show this rational exponent being 1/2. So we find the antiderivative, we add 1, and we divide it by what our new exponent is going to be. We add c, so this is t to the 3/2 power over 3/2 plus c, and then we simplify the expression, we do 2/3 t to the 3/2, and this should be a plus c here. It's just a typo. And then our constant multiple rule, basically if you have a coefficient or if you have a number on the outside of your expression, you can always just kick it outside of the integral and still find the antiderivative like you normally would. So in this case, we had 8 times the power function x to the third power dx. We just put the 8 on the outside, and then we find the antiderivative just like we did in our previous examples, and we keep the 8, and then we simplify it in our final step. Now looking at our sum or difference rules, this basically says that if we have an antiderivative that's written out as a sum or a difference or a combination of the two, you can simply integrate each term in the integrand individually. So you can separate it, you take the integral of each term that is in your integrand expression. And then here's an example. So we have looks like a quadratic function, but we just take the integral, we apply the power rules to each one of these terms individually. So this became, the 3 stayed on the outside, we changed it to w cubed over 3. The 4 was on the outside, we changed it to w squared over 2. And notice that the 5, which was just a constant, when you take the antiderivative, then you will just add the variable onto it. So this is 5w now to the first power over 1, which is why you don't see those 1s, because they aren't necessary. And of course, you still add c onto the end of it. Now looking at some indefinite integrals of our exponential functions, just like the derivative of e to the x power is e to the x power, the antiderivative of e to the x power is still e to the x power, plus, of course, some constant. Then when you take the antiderivative of e to the kx power, where k is some constant, so you have a coefficient here, it's still going to be e to the kx power, but you simply just have to divide it by k. And then, of course, add c onto the end of it. Now, when you take the integral of an exponential function where e is not the base, so a is any number that's greater than 0, and is not 1, then you have a to the x power over the natural log of whatever your exponent is. And then we add c to it. And then if you have a coefficient attached to your variable in the exponent, it still works out the same. You just have the coefficient that's going down in the denominator as well. Now looking at some of our examples, we had 3e to the negative 0.8x. So we can put the 3 on the outside and then just find the integral of our exponential expression. We're going to have to divide by negative 0.8, and we keep the exponential expression intact. And once you simplify it, this is what you are left with. For b, we have another exponential expression, but this time the base is not e, and we still have a coefficient up here attached to our x. So we follow the formula and we keep the exponential expression, and it's over the natural log of the base times the coefficient of the exponent here. And then we add c onto the end as we always do. Then, if you remember in the definition for the power rule, the exponent could not be negative 1, and that's simply because if you start out with a negative 1, then in your next step, when you add 1 to it, you would end up with x to the 0 power. So there's a special rule for when the power function has an exponent of negative 1. You can think of it as also as 1 over your variable, and when you find the antiderivative, it simply becomes the natural log of the absolute value of your variable. In this case, it was x, and the reason why we include the absolute value symbols here is so that the antiderivative rule can be more applicable if you have negative bases. So here are just a couple of examples. We had 7 over x dx, which is the same as 7 times 1 over x. And we just apply our rule. The antiderivative of 1 over x is ln absolute value of x. In b, we have a combination of, we have x to the negative first power here, and we have an exponential expression. So we apply each rule separately. We end up with negative 5 ln absolute value of x minus 1 over 2 e to the negative 2x plus c. And this negative 1/2 came from the coefficient of our exponential expression. Now let's begin to look at a couple of our practice problems. So in the first problem, we are finding the antiderivative of 12x plus 7. And notice that when you have a constant, that is always to be an understood variable raised to the 0 power attached to it, which is the same thing as an understood 1 being there. So when we apply our power rule, we're still going to increase that exponent by 1, and it'll show up in our antiderivative. So first we do 12, which was our coefficient, times 1 over 2 x to the second power. Our new exponent became 2 because we increased it by 1, and we always have to multiply by 1 over our new exponent. So that's why we have 12 times 1/2 x to the second power plus, and this becomes 7x plus c. And when we simplify, we get 6x squared plus 7x plus c. This is our antiderivative. For number 2, we're again trying to find this indefinite integral here. So we just applied a power rule in each step. So our new exponent changed from x to the third, it became x to the fourth. So we have to multiply it by 1 over 4. Our new exponent here is going to increase by 1. That becomes x to the third. And we multiply by 1 over 3. And then we have minus 9. This will be 1 over 2, x to the second, and then plus 3x plus c. And then we just reduce all of our coefficients and simplify our expression. Number 3 is going to be similar. It's just written a little bit different, so I went ahead and did that first step. But when you have expressions written like this, all you need to do is simply distribute across your parentheses and then find the antiderivative of that simplified expression. So we just multiplied in 8x squared and got 8x to the 6th power plus 72x squared. And then from here, you will find the antiderivative just like we did in the first 2 examples. Number 4 is a little bit trickier just because, again, the way that it's written. So here for number 4, we would also have to rewrite the integral first. and then apply our power rules. So we had pi over x to the third, which can be rewritten as pi x to the negative third power, and then we had a radical, which was 2 square root of x, and we just rewrote that as x to the 1/2 power. And then you find the antiderivative using the power rule, just like we did for problems 1, 2, and 3. Just be careful with your fractions here. Notice that we still add 1 to our exponent. That's how we got 3/2. And don't get it mixed up. Still put 1 over whatever you have for your new exponent, and you'll be fine here. And then we just went ahead and simplified it in the last step. And don't forget to add c in all cases for your indefinite integrals. Number 5 is a little bit similar. We had 9 over x. You know that's the same as x to the negative first power. But remember that x to the negative first power is going to change to a natural logarithm. So we first rewrote it as x to the negative first power. Then we found our antiderivatives. We kept those coefficients. So we had 9 times the natural log of the absolute value of x minus 9 times 1/2 e to the 2x plus e to the 0.3 times x. And you're saying, well, how come we didn't do any differentiation rules here? Well, e to the 0.3 is just a constant. So we're just treating this like it was just a constant, so that became a linear function. And then, of course, you add c on to the end of it. And then our last step, we just simplified our expression. For number 6, you have a quotient, but it can be written as a sum of power functions if you separate the numerator and keep the denominators with them. So the first step here is to separate your numerators. So instead of 1 plus 7t to the 4th, we have 1 over 10t plus 7t to the 4th over 10t dt. And then from here, you simplify this expression, you write it as t to the negative first power, and we had t to the 4th over t, which just became t to the 3rd here. And then you find your antiderivative. And of course, in that last step, you simplify it and don't forget to add c. So now we're moving on to our problem number 7, but this is also the same as problem number 10 in your homework assignment. So this one says if the rate of excretion of a biochemical compound is given by this derivative here, the total amount excreted by time t in minutes is the original function. So find an expression for the original function for part A, and then part B says if 0 units are excreted when time is 0, how many units are going to be excreted in 36 minutes? So first, we simply need to find the antiderivative of our function that was given to us, which we apply our rules. We have an exponential function, so we do 1 over that constant times the original exponential expression plus c, and then when we simplify, we end up with this equation here, where c is still a part of it. So this is our answer for part A. And then in part B, it tells us 0 units are excreted when time is 0, when t is 0. So we can plug in 0 for our function, and we know that it's supposed to equal 0. So that means when we plug in 0 for t, our equation is equal to 0. And then we solve this equation now for c. So we have negative e to, which is going to become 0 power, which is just 1. So we have negative 1 plus c equals 0. So we can add 1 to both sides. We get c equals 1. And now that we know what c is, we can plug that into our original equation that we had. So now we don't have a general equation. Now we have the actual equation for our function, where c is no longer a part of it because we know what c is. And then we just go ahead and plug in 36 into our function, and that function value is approximately 0.944. Now, for number 11, we are given another function. It tells us g of x is the per unit abundance growth rate for a population of size x. The researchers considered a simple case and it's telling us that g of x equals a minus bx for constants a and b. So a and b are constants, x is our variable, and g of x equals this expression. So then it says find the integral in this case. And here's our integral that we're trying to evaluate. So we can substitute a minus bx for g of x in our first step. And just like we did in one of our previous problems, we're going to separate our numerator so we can rewrite it as a sum of power functions. So this would be a over x minus b because the x is canceled out in the second term. And now we just apply our anti-differentiation rules. So we end up with a times the natural log of the absolute value of x minus bx plus c. And the answer choice in this problem is, the correct answer is D. And notice that over here in this answer choice, there is no absolute value symbols. And that's because of the context of the problem. Because if we're talking about a population, our population is not going to be negative. So our variable is not going to be negative, nor is it going to be 0. So we don't need that absolute value symbol here in this expression, again, because of the context of the problem. Number 12. So number 12 says under certain conditions we have the number of disease cells, which is the function n of t, at time t increases at this rate. And they tell us some information about our variables. A is the rate of increase at time 0, and k is a constant. So suppose A equals 60, and at 5 days, the cells are growing at a rate of 240 per day. So that tells us that our derivative function n prime of t, our growth rate, is going to be 240 when t equals 5, and a is given to be 60. So a is 60, again, n prime of 5 equals 240. When t is 5, our function equals 240, and we can plug in 5 for t into our equation. The reason why we're doing this is because we want to solve for k first, because k is given to us as a constant, but we don't know what k is. So with this information that they give us in part A, we can solve for k. So we plug in 5 for t, we plug in 60 for a, and we set it equal to 240 as our function value. So we solve this. This turns out to be an exponential equation. We use a logarithm to solve it, and we end up with k being equal to the natural log of 4 divided by 5. And we're going to approximate it. We're rounding it to 5 decimal places, so we end up with 0.27726. And now we can write our function, at least our growth rate function, and we know what k is. So our only variable when we plug it all into our integral is going to be t, which so now we're trying to find the antiderivative of this function. And then also notice that it said to round your exponents to 5 decimal places. Otherwise, we're going to round to 1 decimal. So when we're solving this, we plug in k rounded to 5 decimal places. We apply our exponent rule. So we have 60 over that coefficient times t. So 60 over that coefficient, e to the 0.27726 times t plus c. And now we just need to simplify our coefficient here, and we end up with 216.4, and that's rounded to 1 decimal place. So now here is our function now. This is our function for the population size. So now we go back to part B, and it's telling us to use our answer. We're going back to the second half of part A. It says that 300 cells are present at time t equals 0. So when t is 0, our function equals 300. So we set that equal to our equation when t is 0, and now we can use that to solve for c. So we get 300 equals 216.4 plus c. Again, e raised to the 0 power is just 1, so that goes away. And we have c equals 83.6 after solving this equation. So here is our actual function now. We have all of our variables. We found k. We know what c is. And this is our equation for our population function. And then after that, we just plug in 14 for part B. And that function, and that value turns out to be 10,508 when t is 14. All right, so number 13 says the number of bachelor's degrees conferred has been increasing steadily in recent decades. The rate of change of the number of bachelor's degrees in thousands can be approximated by the following function, where t is the number of years since 1970. So here's the function. They have it written as a derivative. We're looking for b of t, which is going to be our antiderivative, given that about 814,800 degrees were conferred in 1970. So that is our starting point. So that's when t is equal to 0. So first we have our antiderivative here, our antiderivative of the original function. And since they tell us when t is equal to 0, there were 814,800 degrees, we set that equal to 814.8. And the reason why we do 814.8 is because the function is already written in terms of thousands. So we're given this number, so we need to move the decimal over a few places. So we set it equal to our antiderivative that we had. We plug in 0 for t. That makes all of the variables, all of the first few terms go to 0, and then we're just left with 814.8 is equal to c here. So here's our function now for part A, and then we are looking for part B. It says use the formula to project the number of bachelor's degrees that will be conferred in 2018. So since 2008 is 48 years after 1970, we're looking for the function value when t is 48. So we plug 48 into our function and we end up with 2,429.8656. And remember, this is giving us a number that would be in thousands, so we have to convert it back by moving the decimal over again. So we end up with 2,429,866. Number 14 says the approximate rate of change in the number in billions of monthly text messages is given by the equation f prime of t equals 6.9 t minus 16.1. T represents the number of years since 2000. So in 2004, which is 4 years later, when t is equal to 4, there were approximately 9.9 billion monthly text messages. So they tell us our function is in billions, and the number they give us this time is 9.9 already as billions. So we need to find our antiderivative first. We end up with 6.9 over 2t. This should be t squared here, minus 16.1t plus c. And then we plug 4 in, and when 4 is t, our function value equals 9.9. So we plug in 4 for t, we set it equal to 9.9, and then we solve for c. So c equals 19.1, and now we have our function value where 19.1 is plugged in for c. So then we need to figure out for part B, according to our function, how many messages were there in 2009. So t is going to be equal to 9. When we plug in 9 for t into our function, we get 153.65. All right, so now it says for a particular object, the acceleration of the object is given by 7t squared plus 8. And when the velocity, when time is 0, the velocity is 7, and it's asking us to find the velocity function. So just going back to our physics problems, so now since acceleration is the derivative of velocity, that means velocity is going to be the antiderivative of your acceleration. So we need to integrate the acceleration function, which we get here, and then we plug in 0 for t, and we plug in and we set that equal to 7, because when t is equal to 0, our function value is 7, and then we plug in 0 into our equation. So we solve for c, and we get c equals 7. So our velocity function is 7 over 3 t cubed plus 8t plus 7. Then we have another physics type problem where we're looking at, it says a of t equals 15 over 2 times the square root of t plus 6e to the negative t, where the velocity when time is 0 is equal to 6, and the position, remember s is your position function, when time is 0, your position is 11. So they're giving us all of this information. That means we're going to have to find the antiderivative of acceleration, which is going to give us our velocity function. And then we need to find the antiderivative of velocity, which is going to give us our position function. So first we find the antiderivative of the acceleration function. So I rewrote it. Instead of the square root of t, I just put t to the 1/2. And we find our antiderivative. Be careful with your fractions here. Again, remember you're adding 1, so 1/2 plus 1 gives us 3/2 here. And then we make our new coefficient 1 over the new exponent. So then we're going to end up simplifying that. And then here we're just doing the regular exponential function rule when the base is e. And we simplify it, we end up with 5t cubed, 5t to the 3 over 2 power minus 6 e to the negative t plus c. So now we plug in 0 for t. We set it equal to negative 6 based on this information so that we can solve for c in our velocity function. So we plug in 0 for t. We end up getting c equals 0. So c is 0, so our velocity function without c now is just right here, 5t to the 3/2 minus 6e to the negative t. But we're not done yet. We're looking for the position function, so now we need to find the antiderivative of the velocity function. So now we take the antiderivative of this equation. So we end up using our integration rules again. This time we end up with 2t to the 5/2 plus 6e to the negative t plus c. And we still need to solve for c. Remember, when t is 0, the position function equals 11. So we set it equal to 11. We plug in 0 for t, and then we solve for c here. So we have 0 raised to the 5/2 power is 0, so this is gone. E raised to the 0 power is 1, so this will just be 6 plus c on the right side. You subtract 6 from both sides, you end up with c equals 5. And now we're going back here to this equation to just plug in 5 for c, and that is how we get our final answer. S of t equals 2t to the 5/2 plus 6e to the negative t plus 5.